It's actually my first SciPy, and it's been wonderful. So I don't know if you'll think that about my talk. I'm kind of hoping that what you take away from this is never, ever do this. But if you needed to do this for, for some reason, then this might be how you would. Recently, I'm working for a company called 3 Point Science, and we've got a lightning talk this evening. So thanks to them for sending me, and I hope that you like what we have to talk about then. Until recently, I was a postdoc at Western University. I'm now an adjunct there. This is in London, Canada, and working in seismic inversion. And so that's trying to construct a model of the Earth under our feet from what we can learn from seismic waves. And that involves a lot of modeling elastic and acoustic wave equations, and that's an HPC problem. And so we have this interesting conundrum in that we have this old Fortran code. It's got commits in it, well, commits. It has lines of code in it from 1988, and it's been maintained by probably 25 people over, and it has about 25,000 lines of code, so more than 25 years old. And so it has all these features, but I started a postdoc at Western, and I said, the first thing I thought is, well, wouldn't it be really nice to re-implement that in Python and never touch it again? And so I did that, and that's a project called Zephyr. And it doesn't have all the features that Fullwv had, but it is nicer. And so this story is about what I had to do to let our grad students write their new discretizations in Zephyr, but still be able to use the old Fortran code. So I'll talk a little more about motivation briefly, and then some basics. And when I say basics, I mean hello world, but in like 4 languages, so that's useful. And then I'll talk about what we mean when we talk about Python extensions, and so that's calling other code from inside the Python interpreter. And then what we mean when we say embedding. And none of this is particularly new, but it can be tricky to get set up, and it can be useful, but it also adds a lot of complexity. So you got to make sure that it's justified. I've got an example, including some bits of code from our academic code, and you can decide whether you like that or not, because it's a bit messy. And then I'll do some conclusions. So again, the motivation for this is seismic waveform inversion. And that's an intersection of a whole bunch of different fields. So, the motivation is to try and find out something about the Earth. And so that means you need to have a geology background and so on. But the way that we do that is that we model the physics of how waves travel through the Earth. And as they travel through, they pick up information. And that's what we're interested in. And so modeling that's an HPC problem. And then getting something useful out of it is a problem in inverse theory. And we say, okay, we've got all these data, and we think we can predict, on the other hand, what it would look like if we're right about how the Earth behaves. And those don't match. In practice, they never match. We're always wrong. But if we can look at how we're wrong, and maybe we can figure out a way to improve our Earth model. And then we iterate, and hopefully we result in something that gets a paper and people are excited about, or you find some kind of resource, if that's your thing. So, but you can break this down to really kind of 2 steps, and one is modeling the physics, and that's what takes the most time. And then the inverse problem is about really just doing that over and over again until you find the right answer. And so in the seismic case, that's, you set off an explosive, or you have these big vibrating trucks that put some energy into the Earth. And then what happens is that these waves, they propagate through the Earth, and as they go along, they're changed as they bounce off of interfaces, or as they hit something like this slow layer in here, and they get delayed. And so if we measure those on the other side, then they're carrying information about what happened in between. That's the goal, is that we can use that to build an Earth model. The data might look something like this. The Earth model starts out in full waveform inversion like the top, and it gets more detailed, hopefully, to look like the bottom. That's the motivation. And then we can tie something to geology, like we can say, oh, well, this is clearly a sand layer, and this is shale, and that has some meaning for the geologists, which is great. But here's what I'm here to talk about today. And that's, you've got this Fortran code, and it's about 25,000 lines, and it's these lines of code right here. This is the kicker. And I've got my initials on this comment because it's Fortran, so you've got to start with a C. So I'll back up. And the first starting point here is that I'm going to be talking about doing multi-language programming. And the speaker right before me pointed out that's a terrible idea. You shouldn't do this. But if you were going to do this, then you might start with you know, like the most basic Python program, except it's got a couple of cool things. So one is it's got the line at the top, which means that not only can I run it just with the Python interpreter, but I can make it executable and I can run it on its own, and that makes it look like it's compiled code like all the other things I'm going to show you in a minute. And it has a second really important feature, and that's that it has this letter P here, which means we know it's Python. And that'll be important later when we have more than one language messing with our terminal. And so some of you might, I don't know, who here actually has spent a fair bit of time working with Fortran? So that's like probably half the room. So you guys can leave if you want. But I'd love it if you would stay. This is a really basic Fortran program, and these guys all know that actually there should be 6 spaces at the beginning of that line, and I removed them because it was making my words rap, and that was kind of gross. But this is Hello World in Fortran, and it has the all-important fact that it prints an F at the beginning. And the thing that's different about this compared to Python is, of course, we're compiling it first. And I'm using gfortran, which is the Fortran equivalent of the new C compiler. And it turns out that gfortran isn't actually a Fortran compiler at all. It just converts stuff to C, and then it links it with a couple of libraries, and then it compiles the C code, which is great because it means they only have to optimize one compiler. And getting at Python's internals from Fortran is, I suppose it's technically possible, but Fortran doesn't have quite as many features as, at least Fortran 77 doesn't have as many features as C does. So sometimes you might want to have some C in there as well, right? So you do Hello World in C, and it's more complicated because it has all these things that come in. You have to tell it whether you've succeeded or not. 0 means good. And we have to import the print function, but we run this, we compile it with GCC, and we get a similar result. Right? So when you start tying these things in with Python, you have to pick a way to do that. And it could be C types, or it could be F2Py or something like that. Or you could use something like Python, and that's what I've had a fair bit of experience with. I like it. It has its downsides too. So Python is this cool thing that started from a project called Pyrex, and what it does is you can write this code, except it starts with a Y. It looks like Python code, but then what you can do is you can compile it to C, and what that does, it does all the things that Python normally does, and it turns out that's a lot. But it just does it inside a C extension, so like a .so file, right? And there's even an option you can make this executable. So you can give it a main. So you can compile it like this. This is the Python 2 version. And the ridiculous thing is it actually produces, just short of 1,900 lines of C. So that's why Python's slow. But then you can compile that, and the C flags and link flags here are just linking in the Python libraries, because it does require libpython to work. And now you can run it like that, and it really is an executable, and it prints hello world. Okay. So we're talking about extensions. And by this, my timer has stopped. So we talk about extending the Python interpreter, and this is something that probably a lot of people will try at some point. They'll say, well, wouldn't it be nice if Python was a little bit faster, and so you maybe want to access some C code. Something you probably should never try to do is this. So we say, okay, maybe we have a Fortran code, and this is now a subroutine. It looks a lot like the other Fortran code for those of you who aren't familiar with Fortran, except this is how we define a function, more or less. And it's just going to print a message. So it's entirely possible to call Fortran code straight from Python or from Python. But let's suppose we want to access that through C, because we know that gfortran is this compiler that it's actually just creating C code anyway. So there should be a way to combine the two. And it turns out there's some details about the way that strings are handled and arrays are handled and so on. But the biggest difference that you notice is that Fortran functions all have an underscore after the end. This is called name mangling, and it's just so that things don't collide with each other. But this C code can totally link with this Fortran code, and so it can print something from C, and then it can print something from Fortran. So you say, well, what would we call that from? And so we could call that from Python. And so we could print something out, and then we could call C, which we call Fortran, and we get 3 print messages on the same terminal. And we know that Python is really easy to compile into a Python extension. So we could have a Python code, and it could import the Python code, which is actually a .so file that contains all of this stuff. And so we could start a Python, and we could import it, and then we could run it, and it would go from one to the next to the next to the next. And there's no reason you should do this ever, right? Because Python already has a print function. But the point is that you can, and that's sort of entertaining. And so the stack goes like this. It goes through, and each of these is just calling another function pointer. And you can change it up. You could have a slightly different version that goes from Python to Cython. It's a convenient way to compile code from Python. But then goes into the Fortran code, which calls the C code, which calls the Fortran code, right? So that's something that you could do. You probably shouldn't. But it's useful in a lot of cases because there are things like getting away from the Python global interpreter lock, which is important sometimes for HPC code. So maybe the C code that you're running is actually running an OpenMP and it does something multi-threaded. But think about this the other way. If you've got a piece of Fortran code, there's all sorts of things that you couldn't do in the mid-90s. Like, with Python, if you wanted to, I don't know, instead of actually doing a computation, you just call a web service to do that computation. It'd be really easy to do that from Python, comparatively, but it'd be almost impossible to do it from Fortran. And there are lots of other things, plotting inline or working with extension libraries. That can be really hard to do with a legacy code. But of course, in my case, the motivation here is really that we had a couple of grad students who wanted to get work up and running. And how do you do that when you've got all your legacy code? There's 25, 30 years of development in this thing that no one should ever have to interact with. And I spent 10, 12 years interacting with that. But if they can write their new code in Python and just have it work, then that's the motivation, and that's what kind of gets you past the fact that all of this is a terrible idea. So embedding turns this on its head. You say instead of making a shared object and then calling that from Python, you can actually stick the Python interpreter itself inside compiled code. And it turns out to be really fairly simple. There's this high-level API. It's called the very high-level API. So this is what it would look like in C. We import what we need to run this print function here. And everything else is just python.h. So we go in, we get the name of the program, and that's just sort of good practice. And then we call this pyinitialize, and under the hood, that's doing all sorts of exciting things with the Python C API to set up the interpreter namespace and create a place for Python in memory. And then we can print hello world from C, or we can just run this Python code here in the string and have Python print it. And so compiling that is just GCC, or you can put it in a makefile, and you run it, and it just works. But there's a really important subtle point here, and that's that, yes, this string is hard-coded, but there's no reason it needs to be. That's evaluated at runtime by the code that makes up the Python interpreter. So you could just as easily read that code from a file. And that's something that would be very, very hard to do from C or from Fortran. So that level of embedding is not that difficult. It's tricky because it's very, very easy to make mistakes. And it's a complex API. But this is sort of a simplified example that does something very similar to what I did in the full-up application, and I'll talk about this for a few minutes. So this is a Fortran code. Excuse me. The first thing it does, it sets a constant to 100, and then it makes an array of real value numbers, which is just the equivalent to a C floating point number. And then it loops through, and it sets each element in that to the numbers 1 to 100. Right? It's nothing interesting here. It prints some stuff out. It prints out the first 5 of these numbers so that we could see it. And then there's some stuff happens. We don't know what that stuff is yet. And then it just prints the same thing out again. And it's the stuff in between that's interesting. So we see this. It calls something called the NipPy from the name. We kind of figured that might initialize Python. And then it runs this code here to register this array. And I'll explain what that is and show you the basics of that code in a minute. And then it just runs a function. And we don't see that function here, so it must be defined somewhere else. And so what this depends on is that there's a file in the in the directory called extend.py. And it has a function called myFunction, and we see what it's supposed to do is it reads something in. We don't know what that is yet either, because it's defined somewhere else. And then it prints out the first 5 elements, and then it takes the values in the whole array, squares them, and sets the elements in that array to the squared values, and then it returns, right? Prints again. And it's importing something called mymod. So where does that come from? Well, there's some Python code here, and it doesn't really do anything interesting. Yeah, it could just as easily be blank. This is how you would wrap the C print function. And it turns out that everything else that happens is in C. It's not trivial, but the idea is that this mymod is defining a new built-in that's actually just built in only in this special interpreter that we're running inside the Fortran code, and that we can do pretty much whatever we want with that. And so this register 1D array thing, this is where the magic happens, and this is some messy C code. But I just want to draw your attention to a few things. So we have a module name that we define, and we have a name of a file that we're going to be interested in reading. And this run.py, the only thing you really need to know is this line here. It's the same run that we did before. The rest is just about going from Fortran strings to C strings. So this lets us run arbitrary Python code from Fortran. It's just really a thin wrapper. And the init.py does a few things. It runs pyinitialize. It does the same equivalent for the NumPy API. And then it takes that module that we defined in the Python code, which has been compiled in, and it gets a reference to it, to this py object, which is like a pointer to an arbitrary Python object. It creates a Boolean. It gets something from the C preprocessor to say whether this is debug or not. And then it does a setAttr. So this is what setAttr looks like in the CPython API. And so even though this is compiled code, you can do the sorts of things we're used to doing in Python. We can bind something to that module that built in on the fly. And we could open a file that contains some Python source code, and then we could run that. And that runs in the interpreter namespace. And so if you use something like Paraview, it has a terminal in there. And it's running Python code that you type in. The only difference here is that there's no user interface. So then there's some code for handling string conversion. But the real trick is this way of registering an array. So what you can do is you can get, when you call this from Fortran, you give it a name, and you give it a Fortran variable, which is like a pointer. So it's pointing at the location in memory where this data is. And then you say, how long is it? And it constructs a NumPy array around that. But instead of making a new empty array full of zeros or something like that, it just points at the location in Fortran memory, which is really, it's bad isolation. But if all you're trying to do is have a way of overriding bits and pieces of the Fortran code, it kind of makes sense. So then what it does is it gets a reference to the module, and it binds that to that label that we got from the Fortran code. So now we can go through and take whatever particular things we want to access from Python and bind them in from the Fortran code. And we can actually change the elements on the fly. So we can call into Python code, we can do whatever we want, and that could be anything Python can do. And we just pack the results back into Fortran. And it goes on its merry way, and it's just that instead of doing the matrix factorization in Fortran, it happens to have been done by mumps or SuperLU or something like that. So this is incredibly complicated, but here's the upshot. This is all it takes to take Zephyr, which is our Python code, and replace the Fortran matrix factorization and solving code with that from Zephyr, which uses external solver libraries. And there's this really entertaining thing that it's actually about 3 times as fast because the external libraries are much faster than the code some grad student wrote in 1995. So we go through, and instead of running Fortran code, we set up a Python object and bind it to a global. And then when we want to actually solve it, we just pull the right-hand side out of the Fortran memory space, do some kind of a pseudo matrix multiplication, and then pack the result back in. And this is what I'm actually most proud of. And you can question whether I should be. But what this code does is instead says we're going to use something defined on the built-in module. So we're going to have it give us a sparse matrix. And this is the Python code it takes to have Fortran compute the matrix coefficients and then pack them into a SciPy sparse matrix. So then you're going Fortran, C, Python, Python, Fortran, getting back a sparse matrix and doing whatever you want with it. This is all motivated by the ability to have this be the new way of doing things that the new grad students run across. This is forward modeling in the Python code. And I'd love if you check it out. It's called Zephyr. So there's what I'd like your reaction to be is, there's this scene in Star Wars when they, no, that's impossible. That's the correct response. But it's useful for a few things. It's great if you're having a beer with somebody and you are telling a story. And it turns out there are some neat things, like the Fortran code runs in MPI, but that's actually not a big deal because you just have more than one Python interpreter and you can run all in parallel. So if the Fortran code's parallelized, so is Python automatically, which is kind of nice. The big upshot is that our grad students don't have to spend a lot of time learning Fortran, which is a lot less useful to them in today's world. So, and hopefully that's worth it. Thank you.
Thank you. We have about 5 minutes for questions. So who wants to start? Here we go.
So this is very impressive and nightmarish. And
yes, both. Well, at least the second.
I'm curious so the examples you showed I think are straightforward for this, but we've done a little bit of this with the equivalent in Swig. Mm-hmm. And we have had some difficulty with some terrifying subtleties involving object ownership and things going out of scope in Python and getting deallocated and having their compiled language reference disappear, resulting in seg faults that take a long time to figure out. Is that part of the fragility of this, or do you have a way of dealing with that?
I think that's probably, the toughest part. That the advantage here is that what I've done is, so for those of you who don't know, Python has a garbage collector. And what happens is each time you create a new reference to a Python object, so each time you pass it to something, it increases the count of the number of times that object is referenced. And if that count ever goes to 0, then it gets thrown away. And the idea is that you don't actually have to worry about that in Python, but in the C side you do. And so that's what this pydecref is it's throwing away one of those references. I think I get around that partially because I create this built-in module, and then I bind everything to it, so it never goes away. So there's always a reference. I guess that's cheating, but it turns out almost all these things are in common blocks because that was all the rage in the early 90s. And so it was already a terrible scoping issue anyway, so we may as well make it worse. And
Next question. I have just a simple comment. You can use I2C binding in Fortran, and that allows you to ensure that the compiler itself checks the types, and you don't have to use the underscore at the end of when you call into Fortran. So you can literally skip the C part. So you write Fortran, use I2C binding, and then you write Python directly and calling from Python.
Yeah, that makes sense.
But of course, when you want to call Python from Fortran, then you are still stuck with C. So
yeah, and most of the complexity here is in the C code. I think, which actually the Fortran code there's very little additional Fortran code. Mostly it's just a big subroutine that registers all the variables, so in the real app.
Thank you. If there are no more questions, let's thank the speaker again.